So we've covered some concept stuff, but the new topic that I really want to introduce for this week is threads. And to properly introduce that, I want to write some code that is going to create some threads. So let's go ahead and open up a file. I'm going to call it create.c because it creates a thread, and then we're going to include some headers. If I can spell the headers. So these first two headers you should recognize, and then the third header is the pthread header. This is for POSIX threads, and is the standard thread API that gets used on sort of Unix-style platforms in the modern day. So we're going to go ahead and write a main function. And in the main function, which requires curly brackets, not a square bracket, we want to start some threads. All right, so there's steps here: pthread, tthreads, nn. So we're going to allocate an array that is going to store 4 threads. A thread is some sort of pthread t structure, or maybe pthread t is just an alias for an integer. We don't know. We don't need to know. A pthread t is a thread handle. Then we're going to say main starting some number of threads. And then for int I is 0, I is less than n, plus plus I, we're going to say pthread create and then we're going to pass in some stuff. Let's pull up the man page for pthread create. So pthread create is going to require a thread handle. That's what we're going to fill in. So threads II takes a pointer to a thread, and then it's going to initialize that with the new thread. Then we have some attributes. Attributes can just be a 0. Then we have a function pointer. So this is going to be a function with the following signature. It returns a void pointer. Then it takes a void pointer as an argument. So we have to pass a function with that signature. Just go ahead and pass it by name. And then it's going to take an argument. And we'll figure out what argument we want it to take in a second. Then we're going to go ahead and say assert rv is 0, because in the man page, oh, I lost my man page. In the man page, it says, it says a bunch of stuff. Return value. Return value, there we go. On success, pthread create returns 0. On error, it returns an error number. So if it returns 0, we're good. Now the work that I want to do here is I just want to go ahead and have, I want to go ahead and pass in a number, and then I want to add the thread number. So, in fact, what I want to pass in is the thread number. So we're going to go ahead and pass in II here as the thread number. It's the argument that we're going to pass to the thread. Now, unfortunately, we can't quite pass in II because II is an integer, and a thread takes a void pointer. So we're going to take the address of that and cast it to void pointer. And now that'll pass the address of that variable, and so we can have access to that variable in the thread if we go ahead and cast back out. So we're going to say int x is going to be the thing that we get if we cast to int pointer, that thread arg, and then we dereference it. Now we'll print out that value that we found. And then let's go ahead and just double that value. So we're going to say that the number that we got So this is also going to return a void pointer, so let's go ahead and return that void pointer. But let's return our thread number doubled. So this is going to spawn 10 threads, numbered 0 through 9, and we want to return 0, 2, 4, 8, etc. Again, we have to return it as a void pointer. So I'm just going to go ahead and return the void pointer that we already have. So we're going to cast this to int pointer. And then dereference it, and we're going to add that value x. All right, next thing that we're going to do is we are going to print out that we've started that number of threads, and then we're going to wait for all our threads to finish, just like waiting with processes. Here we have a function called pthreadJoin, which will join a thread. So let's look at the man page for that. It takes a thread, so we want threads II, and then it's going to take a void pointer return value. So we need a void pointer, it's going to be the pointer to the return value, and then we're going to pass in the address of the void pointer variable so that pthreadJoin can fill in the return value, which is going to be a pointer. So then we'll assert rv is 0, and then say that the result is going to be the thing that we get if we dereference the int pointer, ret. So there's our test program, and I want you to take a careful look at this test program and try to predict what's going to happen when we run it. And quick question, do you think this is going to do the thing that it appears to be intended to do, or is something going to go wrong? If something goes wrong, what's going to go wrong and why? Let's go ahead and compile this, create.c. We need lp thread, and then we'll run create, and it says started 10 threads, thread 1 we're in a thread, thread 3 we're in a thread, thread 7 we're in a thread. In the main function it says we've started 10 threads. Then it's going to say thread 15 we're in a thread. Thread 0 and 1 returned, we joined them, and we got back values of 0 times 2 is 15, 1 times 2 is 30, and then the program didn't terminate, it's just sort of frozen. So there's something unfortunately wrong here. Let's run this again and see if we get the same result. No. This time we get threads 2, 4, 9, and 19, and we get results from threads 0, 1, and 2 of 19, 38, and 38, which are not the correct values at all. Now, of course, the problem here is that this value that we're passing into the thread isn't the thread number. It's not a number from 0 to 9. It is a pointer to the thread number, but not a pointer to the thread number. It's a pointer to this loop index, II. And if we pass a pointer to this loop index II, and then the thread executes concurrently, the new thread executes concurrently with the main thread, we can actually end up with situations where the loop index gets mutated before the loop is done. And that's why we see different results at all. So we have an awful race condition, and the race condition is on this loop variable that is conceptually on the stack in main. So I want to, rather than having a single integer, I'd like to have an integer for each thread. So let's go ahead and make an array of ints called nums. Say nums II is II. And then rather than passing the loop variable itself here, we're going to go ahead and pass that slot in the array. And what that will do is make it so that, so before we create the thread, we are assigning a value to this array. So that slot of the array gets written once before there's any concurrent access to it. And then after it gets written, we start the thread. After we start the thread is going to modify the value in that array index, but there's no other thread accessing it concurrently. Then when we join, where again, this ret variable is going to be a reference to that, that array element, which is on the stack in main, so that's all fine. And then we print it out, and again, there's no concurrent access to individual slots. There's concurrent access to different slots because threads are going to be operating each on a different slot, but there's no data race there. So let's see if just doing that fixes the problem. So now we have exactly the right behavior here. We start 10 threads, 0, 1, 2, 6. The threads are running concurrently. We don't necessarily get output in order. That's fine. We're spawning 10 threads for a total of 11. On this machine that I'm working on, there are 8 hardware processor cores and 16 hardware threads. So we can conceptually run up to 16 threads sort of in parallel or concurrently in hardware. So we don't necessarily know that, like, thread 6 won't start before thread 3. We know it was created first. The lower number thread was created first, but the higher number thread in this case got scheduled enough first that it printed sooner. So yeah, that is the absolute basics of threads. And this demonstrates the thing that we saw in the sort of virtual memory diagram differentiating threads from processes, and that is that all memory in a threaded program is shared memory during concurrent execution. The place where we had a data race was on the stack for the main thread. It was a loop index on the stack in the main thread, and that created a horrible mess, which luckily we were able to fix. So I'll be back in a second with some more thread examples.